Alrighty. Hello, everyone. It is Tuesday, June 17th, 7:05 p.m. We're going to continue on with binary trees. Yesterday, I want to read what I did yesterday, because yesterday I remember I just kind of was not feeling it, kind of gave it and quit early. I was tired, really tired today. I'm still a little tired today. Try to go to bed early today, earlier. See if I can rest up, so I'll be feeling hopefully much better tomorrow. But take a look at this. Okay, that makes sense. Okay. This one I think I have to iteratively go through. This is BFS, breadth first search, which I have not done BFS in forever. So, alright, let's try to. So I can either do the math for this, or I can do this a specific way. Let's see if I can figure that out. Okay. You know what? Screw that. Screw that. So okay, we're gonna hit 1 first, the root. We're gonna put that into our queue. And then we're going to empty that and put it into new queue. Okay, so we're going to empty this, going to put it over here, 1, and then our new queue is 2, 3. Okay? And then we're going to empty it, but put things in the new queue. So we're gonna now put 2, 4, 5, 3, 6, 7. Okay, that's how we're gonna do it. See if that works. So basically, I'm gonna do kind of like a double queue operation. How do I do BFS properly? guess we're gonna do pop. We're gonna do a Q pop, which is the first value. Which is this. So if it's not if it's not a null, then we're going to continue. This is probably a little archaic. We'll see if this works. I'm running a double Q situation. Okay. So just kind of doubling up the space is not bad. I mean, sorry, this is not good practice. But, you know, we do what we gotta do. This is bad. I hate this, but we're gonna just do this. Definitely ignore what I'm doing right now. This is horrible practice because I'm not paying attention to how I'm supposed to do this right now. This is like spaghetti all over the place. An interviewer would literally fail me in a heartbeat. This is bad. Okay. Yeah, this is really messy. It's the one runtime error. Type is not. Whoa. What am I doing with this? Is that the problem? What's the issue? Oh. I mean, it worked. It's really tacky. You can do TFS on that? What? I don't like the way. I'm sorry. I'm gonna be a hater, but I do not like the way he does his variables. They're so unreadable. I mean, realistically speaking, this Q1, Q2 is also pretty unreadable, so I don't really have much to say. I don't really have much of an argument going for myself, but yeah. I love his tutorials, though. I mean, he really does break it down. So I'm not saying it's bad. It's just, my brain does not jive well with those variable naming conventions. Binary tree right side view. Given the root of a binary tree, imagine yourself standing on the right side of it, returning values and nodes you can see. Woohoo! Okay, that is interesting. My guess is we do what we literally just did, but we return the last one. That's pretty cool. Screw it. Let's hold on. Let me see. No. I actually kind of like my double Q approach. Hate me if you want. Okay, so my thought process here. Same thing. We're gonna have run a double queue. Q1 is going to be running through the current layer, and then Q2 is storing the next layer, and then it swaps it. And then what we're gonna do basically is we're gonna run a checker, basically saying, hey, if right now Q1 is empty, that must mean that this value that we're looking at right now, this pop value that we're holding, has to be the last one because it's the last one we popped, meaning that's the rightmost side. But that doesn't take into effect nulls, so we're not gonna do nulls. Yes, we are. Yes, we are. We're gonna avoid nulls this time. Just to make this process a lot cleaner, don't have to worry about running through nulls. And then I'm gonna run one more question. I'm basically say if Q1 is empty right now, then levels.append pops.value. I like how he puts these problems back to back, they're very similar. That's pretty nice of him. That's pretty cool, brother. He's kind of teaching you how to think, algorithmically speaking. Appreciate that. That makes a lot of sense. Because if I didn't have that, I probably would have been so confused on how to solve that. Give it a binary tree root. A node x in the tree is named good if in the path from root to x there are no nodes with value greater than x. Return the number good, number of good nodes in the binary tree. Okay, so this is good. This is good. This is good. Oh, and root is good. I think this could be pretty easy. Yeah, Max. So I'm gonna say def num number of good. Number of goods. I'm gonna say node, and we're gonna put max. No, I'm not gonna do max. I'm gonna do current max, and we're going to return an integer. So the way I'm gonna run this is basically I'm gonna drop in the node and the current maximum it has at this moment in time. And yeah, so So there has to be at least a root, thankfully. So I'm gonna run this. I'm gonna say if node.value is greater than or equals to current max, then we're gonna return 1 plus number of hold up. If node equals none, return 0. Let's make that clear. Plus a number of goods with node dot left and node dot value. Oh wait. Wait. Oh, we're good. Yeah, no, this is fine. Because node dot value should be the current max because it's greater than or equal to. Okay. Else return current max. Okay. Oops. And then I'm going to return number of goods, and we're going to do root and root dot value. Okay, let's test it out, see if that works. Okay, it accepts. Submit. There you go. And we were on the faster side. That one was pretty easy. So if you're confused on what was happening here, basically if the current node's value is greater than or equal to the current maximum, then that's a good value. And we can just return 1, which counts that as a good value, plus then we're going to kind of recursively dig down and see if there's any more below us. If the value is less than the current maximum, that means it's not a good value because there's some value above it that is greater. So we don't return 1 plus it. It would be 0 plus it, which you don't have to show the 0. And we're still going to have to dig down to see if there's anything else below it. So this digging down, basically, now I'm here, I'm at this 3. It's a good value. Okay, I'll take the left value. So now I dig down to the left value, and I keep the current maximum, which is 3. Well, 1 is not greater than or equal to 3, so therefore this is gonna be return 0, but I have to dig down one more time. I hit this 3, and 3 is greater than or equal to 3, so then it's 1 plus 0, and there's also a null here, which is 0. So 1 plus 0 plus 0 plus 1. That makes 2 for this side, and then if you do the math over here, there's 2 more over here, which makes a total of 4. So that's that problem. Okay, let's do another one. Given the root of a binary tree, determine if it is a valid search tree. Okay. So this says there has to be at least one node, so I don't have to worry about any empty nodes, which is good. Okay. If left node is not none, I'm gonna say result equals true. If left node dot value, it has to be less than. There can't be any equals. Yeah. Is less than node dot value. We're good. Like, you know what? Hold on. And then, yeah, this is here. We're just going to return false. Just get rid of the result. We don't need that. Else, we'll just return recursive of left node and recursive of right node. Okay, and then all I have to do is return recursive of root. Okay, let's check that, see if that works. Here you go. Okay, so before I submit this, it might not fully work, but my thought process here is basically, we know that the root is never none, so I could technically get rid of this and add in an extra checker, basically saying if left node is none, then don't borrow it in, but I'm not going to. Just because I think this coding convention is just much more clear and can catch more problems, so I think realistically I would like this more. What I'm doing then is I'm grabbing the left node and the right node. So if the left node is not null, okay, that's the first checker. Meaning if it is null, then we just ignore it, because a null value can't have any sort of meaningful inheritance to the situation. So a null value won't be greater than or equal or less than, doesn't matter. But if it's not null and the left value is greater than the current value, then that can't be right. That's breaking the rules. If the right node is not null and it is less than or equal to the current value, that can't be right. That has to be incorrect. It can't be less than or equal to. If neither of those are true, which means the BST is safe on the current level, then we are going to go basically one level deeper, check the left node and the right node. And we're going to return whatever we receive from those. And at the very end, we're just going to return the root. Or we're going to return the recursion on the root. So that'll do down. We got an incorrect answer. So my logic was flawed. So I outputted true here. So 5, 4, 6. That's good. 6, 3, 7. Ooh. Dang. Okay. Okay, here we go. Alright. Now I'm afraid we are cooking. didn't even think about that. I thought this was gonna be stupid easy. Yes, this is very true. My first thought on how to solve this is using a previous value. Okay, so I'm gonna do this. This is going to be a kind of a janky thing. So previous can be null, and that's valid for it to be null. So basically, I'm gonna say if previous is equal to none, that's valid. We're fine with that. Or if it's not, if it's not none, then it has to be certain situations. It's gonna have to be like previous dot value. It has to be oh. Crap, I remember this. Oh, wait. This is not a binary search tree. Five, 9, 2, 4, 1, 6, 10. Okay. So this left has to be greater, and this left has to be less. If it's on the right side, no matter what, it has to be greater. So if it's the right node, everything has to be greater. Oh, wait, is this using the current max? Dude, hold up. Are we doing current max right now? I don't know how I would apply that though. I'm gonna use some hints. Right. We start with the interval negative infinity and positive infinity for the roots. As we traverse, when checking the left subtree, we update the maximum value limit because all the values in the left tree must be less than the current node's value. Conversely, when checking the left, we update the This is a good problem. Okay. There you go. Go through here. Okay. Alright, okay, so basically what this is doing, so if min or max is none, we treat that as infinity, as in always going to be greater than or less than, like no matter what. It's the rounds. I don't need to write out infinity. I know some people will import infinity. Infinity can, for all intents and purposes, is literally null because infinity is just a concept. It's not an actual value. Same as null. Well, null is a value, but whatever. I digress. So if minimum value is infinity, negative infinity, then we're good. But if it's not, then we have to check. If minimum value is less than the node, well then that means the current node should be safe. So, for example, in this instance, if I'm at 3, minimum value should be 2. Everything on this side has to be greater than 2. And it is. So, right here, minimum value is 5. Everything on this side has to be greater than 5. It's not. But if it was, let's say this was 3, then it ran true, then we would check over here. And then we would say everything on this side has to be greater than the minimum side of a minimum value of 4. So we keep updating the minimum as we go right, and then we do the maximum if we go left. So it has to be less than the maximum. So right now the maximum is 4, less than 4, we're good. So that comes from neat. I didn't really think of that myself. That's a very smart way of going about that. I liked it a lot. That is pretty neat. Okay. Let's see. Hello. Sorry, I gotta take this real quick. Sorry, had to respond back to some messages. Apologies about the absence. Oh, I was about to be like, this is easy. It's not easy. This is definitely not easy. This is actually really hard. What was the last one? Validate? Damn, how would I do this? Oh, so we're going to check every single thing O of n. Okay. A nice solution would be store the values in an array and then sort it. So what do I do? Oh. Oh, okay. So this is dumb. Is there really not a better way? Is this supposed to be done in O of n? If the BST is modified often, i.e. we can do insert and delete operations. I have no idea. Okay. Basically what I'm thinking, from what it sounds like, we're just going to store into an array through BST, which will give us the correct order, and then we just return the ith index. Or ith minus 1 index. What are you talking about? Okay, maybe I'm thinking this is too easy because like I'm confused as to like what are we talking about right now? Def recursion node, then non-local array. If node equals none, then we're just gonna return. And then I'm gonna say recursion of node dot left, and then recursion of node dot right, and then I'm gonna say array dot append node dot value, and then I'm going to I'm gonna do recursion of root, and then return array of k minus 1. Wrong answer. Blah, 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 blah. Okay. I'm confused. Is this not a DFS? I thought. Oh. Yeah, no. This is not the proper order. Whoops. Gosh. So silly. That's how I do it. I don't know what kind of other solution there would be. Morse travel. Oh, here we go. Here we go. Here we go. This is what I'm talking about. This is what I'm talking about. Space complexity O of 1. Okay, actually, what is this? I'm not touching that. Never mind. Y'all can have that. Not me, though. Hell no! Not touching that. I hate Iterative. I hate it so much. With the bottom of my heart, I hate Iterative. Okay. Construct a binary tree from a pre-order and in-order traversal. Given two integer arrays. Pre-order and order. Damn, sorry. What's up, big guy? Does pre-order just BST? This is BST. This is breadth for search. Okay. No, this is depth. This is breadth. So, given breadth for search and depth for search, I have to figure this out. Oh, hey, buddy. Hi, Max. Cat just jumped to my lap. What's up, bro? I know I'm coding. I'm coding right now. What are we coding? What's up, bro? You're a good boy. Mwah. I have no idea how I would do this. Like, zilch. Not even a single clue on how I would do this. Yeah. Because, like, obviously we want to use both, but, like, confused. What's the time complexity on this? It's like O of n. You can observe that in order helps. That's valid. I could do. See if I can work this out in my head. Stop. Relax. Hey, relax. Relax. Yeah, actually, no, I don't know. This is so confusing. Yeah, I'm not gonna lie, I'm very confused on how to solve this. And honestly, I've already kind of done enough problems today. I'm probably gonna just leave this up to another day. Today we did 1, 2, 3, 4, 5 problems, so we did pretty good today. 55. So yeah, I'm gonna call it there. It's been almost an hour. Thank you for watching, and I'll see y'all tomorrow.